one of the things we talked about in the lecture. Now, we just mentioned this, and you'll need to look back at the notes to make sure that you caught this. Is a concept called stacks or call stacks, and this is a way of managing memory in programs that call different functions. Now, in this tutorial, we're going to go through an explicit example of a simple function. And if you want to follow along, you can just look at the tutorials for week 4 and look at the call stacks. Okay, so what the heck is a call stack? Well, when you call any function, a lot of functions, they need to store values and store things in memory. And what happens is the system, and this is implemented in all computing languages, sets aside space in the memory on your computer for that function to do what it has to do that work you want it to do. And we call these chunks of memory stack frames or function frames or just a stack for short. And because of the nature of programs, sometimes we call a lot of functions. More than one function's stack frame can exist in memory at a given time. So, for example, if you have a main program, you write a main, and it calls another function called move, and move then calls direction. All three of those functions have open frames until their work is done. Okay. Now, we metaphorize these memory frames as being arranged in a stack, and we're going to exploit that metaphor with a visual representation of it here directly. And now the frame for the most recently called function is always at the top of the stack. Okay, that's the way this metaphor works. And when a new function's called, the new frame for that function is pushed onto the top of the stack, and that's the new active frame in memory. Well, when a function finishes its work, we pop the frame off of the stack, and the frame immediately below it becomes the new active frame. Okay, so this function, if we're waiting for other functions to do its work, when those functions that do their work are gone, they get popped off, and we're back to the function that needed to do the work in the first place, and it carries on. That's the idea here. So let's kind of look at a little program. Up here, we're defining a little routine called fact. Fact for factorial takes an integer, and then we've got an if-else. So if the integer that's passed is equivalent to 1, we return 1, or else, and that's the finished state for this little routine, or else we return factorial calculation, which is n times fact n minus 1. Now, there is a special name for a function that calls itself. We refer to this as a recursive function, and this is a perfect example of it, and it's the one we cover in the notes, so make sure and look back at that. So we define this function up here, and now we've defined a main function down here, and we call print, another function, and in print we call fact. And here we're passing a value to fact. So we're going to calculate factorial of 5. You can do the math yourself. It comes out to 120. And we've specified a variable, an integer that we want to print with a new line that's going to pick up on the value of factorial 5. All right, so that's what this is. So when we run this, the first function that gets called is main. So there's a frame for main, and that's the whole stack. But then what do? We're calling print inside main, so we add a frame for print, and that becomes the top of the stack, the next active function. And then what are we going to do? Well, I hope you can see pretty clearly that we're going to call the fact function right here, And that's going to be added as a frame on now the top of the stack, and we've passed the value in the factorial. And then what's going to happen? Well, we're going to run through the factorial function, the fact function, and we see that n is not equivalent to 1, so we're going to go on to the else, and we're going to, now here is the interesting thing on this particular example for the recursive program. We've got an open frame for fact 5, but here we're calling factorial that takes n minus 1. And it's n times factorial n minus 1 that it calls. So here we have a call to fact with a 4. So we have to add an open frame for that second call of fact here. And because our ending condition has not been met, fact now in and now equals some value other than 1. At the moment, we're going to go through the routine again, and we're going to call fact again, this time with 3, n minus 1. Okay, so we haven't changed the value of n. It was 4. Now it's n minus 1 again. And we're going to repeat this several times. You can see we're going to do it for fact equals 2. We're going to do it for fact equals 1. And oh, hey, now we've hit our ending condition. And we're going to start peeling off the fact frames. And now we're down to our print frame again, which has some work to do. What work does it have to do? Well, it's going to print the value that was returned for factorial 5, which is 120. And once print does its work, we peel it off and we're just back to main, which will eventually close. Now that's the concept of a call stack, or just a stack for short. And this is going to be very important to at least understand as a concept. We won't be doing a lot of deep diving in memory management. C is very, very forgiving, and actually more modern languages are also very forgiving in this way, where you don't explicitly manage it. But actually we can do some very powerful things in C, and we will touch on that later on. So this core concept is important to get down now. And that's all that I have to say about that.